Hi and welcome everybody to the lecture titled The Big Picture of Physical Layer Security Techniques Against Wireless Passive Eavesdropping. In today's lecture, we are going to classify physical layer security techniques into two main major categories and then deep dive into the concept of each one of them, the main concept, the main idea, then discuss the enabling technologies in each category, then mention and state the key merits, advantages of each one of these categories, and then discuss the demerits, and then provide some notes, remarks, and lessons related to each one of these categories. Briefly, we classify physical layer security techniques in this domain into two categories. The first category is the category related to signal to interference noise ratio based approach. We call it, between two parentheses, we call it keyless. So in this approach, we can provide security without sharing keys between the transmitter and receiver. And this is very interesting. So this word keyless means without sharing keys between the transmitter and receiver, you are able to provide security. And the other category is complexity-based approach or key-based approach. So the idea here is you try to extract the key from the random channel, and then you can use this key in an asymmetric encryption method or symmetric encryption method. So you can use it as a public key, private key, or as a shared key between the transmitter and receiver. The main idea here is to be able to extract a key from the shared wireless channel between the transmitter and receiver. And then it's up to you to use this key in an approach that's similar to advanced encryption standard, for example, where you have a common shared key between the transmitter and receiver, and they use it to encrypt and decrypt their data consequently. Or you can use it as a public and private key approach, where you use asymmetric encryption and you share it between the if you want to send your data to a certain user, you use the public key of that user, and then that user uses his private key, which is extracted from the channel to decrypt the data. Now let's compare them in terms of concept. The concept of keyless, so SINR based, which is keyless. Let's agree among each other to name it keyless for simplicity. The keyless approach, where you don't have a shared key between the transmitter and receiver, let's assume like that. The approach is mainly focusing on providing secrecy. And providing secrecy in this approach is possible when Eve's signal to interference noise ratio is naturally or artificially made lower than Bob's SINR. This is very interesting. You need not only take this as a blueprint of the meaning of keyless approach in physical layer security, but you need to understand its meaning practically. And here we need to explain it with an example. So we said that in this concept, keyless approach in physical layer security, Eve's signal to interference noise ratio is naturally due to the channel equality or artificially due to a special technique that you design made lower than Bob's SINR. The first thing we need to understand is SINR. What do we mean by SINR? Signal to interference noise ratio. S means signal, I means interference, noise ratio. So as the name implies, it's a ratio. Ratio means there is a numerator and denominator. Numerator, in the numerator we put the signal power. The signal is power, P, signal power. And in the denominator we put what? The interference power, I, power, plus noise power. So signal power over interference power and noise power. Now we know that signal power is affected by the power amplifier and how much current you drive into the circuit of your transmitter and the gain of the antenna and so on. This improves the power of the signal. And for the interference power, interference is when we are close to other base stations or other access points or other users or other devices who are transmitting on the same frequency that we transmit over, and it can interfere with our signal in this case because they are using the same frequency, transmitting at the same time, and the signal has some power. So this will affect the signal to interference noise ratio, which is related to the receiver sensitivity. So the higher the value of the signal to interference noise ratio, the better the signal quality will be. And this means that it got lower interference, lower noise, or higher signal power. So signal power, we understand what affects it. Noise, we understand it comes from the environment, and it basically, it's also related to the path loss and how far you are from the base station. And we have the interference, which is coming from the other users in the network who are transmitting at the same time. Now, okay, we briefly understood what's signal to interference noise ratio, and this interference is a domain by itself where you have so many different types of interference. You have intersymbol interference, intercarrier interference, intercell interference, interchannel interference, interband interference, interantenna interference, co-channel interference, adjacent channel interference. There are so many different types of interference, and all these types of interference can be represented by this term, I power, IB. So this, if we put E here for the signal to noise ratio, if we put here signal to interference noise ratio E, we mean it's for Bob, for Eve. And if we put instead of it B, it means for Bob. Why we say Eve and Bob? Because we said in the previous lectures, we model our physical air security systems as having a transmitter in one side and receiver on the other side, and eavesdropper in this side, which is the malicious user, Eve. So Eve, we transmit our signal from the transmitter to the receiver. This is Bob. This is Alice. We assume always the transmitter, we assume it to be Alice, and the receiver to be Bob, and the malicious user to be Eve. So we take the first letter of each of these users, E here for Eve, and B for Bob. And we have Alice the transmitter. We try to measure the signal to interference noise ratio is a quantity that you can measure it with your device, your device can measure it. And we need to measure it here and here. Now, to be able to provide physical air security, the signal quality at Bob should be better than that at Eve. When Eve's S sign R is naturally made lower than Bob's S sign R, we have security. So which means that when you subtract the signal to interference noise ratio of Bob minus the signal to noise interference noise ratio of Eve, this should be a positive quantity. When it's a positive quantity, you will be able to provide physical air security naturally. In that case, you can send your information at a rate where Eve cannot detect it, cannot decode it. That's the idea. So, but here we have two words, naturally or artificially. How can you make Eve's S sign R, Eve here, S sign R, lower than Bob's S sign R? The value that I measure here is sin R, and the value that I measure here is sin R. I want it here to be lower, which means the one at pop is greater and here lower. How can I do that? We have two ways. The first way is naturally. Naturally means if the receiver pop is closer to the base station, in this case, if the receiver pop is closer to the base station, Alice, in this case, the signal to interference noise ratio is greater than Eve because Eve is farther, the receiver R pop is closer, and we know that the path loss, the distance affects on the path loss, and the more distance we have from the base station, the more path loss, the more suppression to the power received at the receiver, and therefore the lower the S sin R will be. Now, when Eve is far, it means it got lower S sin R. When a pop is close to the base station, it means it got higher S sin R. So if this is the case, then in this case, we can provide physical air security. However, if Bob and Eve, they have relatively equal or close signal to interference noise ratio. If they relatively have equal or close signal to what will happen in this case? Or if Eve's signal to interference noise ratio is better than Bob, in this case, you cannot provide physical air security naturally. Here where you need to think as a researcher, as an engineer, as a technician, as a developer. What can I do? What can I do to make Eve's signal to noise ratio worse or lower than that of Bob, even though naturally Eve is closer to Alice? This is where we need to artificially, in an intelligent manner, design a technique that can degrade the signal to noise ratio of Eve by maybe injecting noise, adding noise, or focusing the beam of interference to Eve so that the signal to interference noise ratio is lower. So this is the idea here. Clear? Any questions? Now let's go to the enabling techniques, the techniques that can allow you to make Eve's S sin R worse than Bob's S sin R, which means there is a positive difference between Bob's and Eve's S sin R. What are the techniques that we can? We have the first technique called channel coding. Here, the first technique is channel coding. The second technique is called channel-based adaptation. And the third case is injection of artificial noise interfering signals. So the first technique is you have your data bits, zeros and ones, sequence of zeros and ones, and the transmitter tries to encode them in such a way, encode them in a way that the coding process is function of Bob's channel behavior. So in this case, since Bob knows his own channel and Eve doesn't know Bob's channel, Bob's only Bob will be able to decode his signal while Eve will not be able to decode it. This is one approach. The channel-based adaptation approach, in this case, you have your transmitter and you have your receiver and you have eavesdropper. Now we know that the channel, in the previous lecture when I was talking about the channel and trying to explain the characteristics of the channel and the features and specifications that we usually exploit in the channel in order to provide physical air security, we said at one point that the channel is random is fluctuating usually like this. So let's assume this Bob's channel. This is the representation of Bob channel. And Eve got another channel. Let's put it in another color like this. This is Eve's channel after measurements by the device. So as you can see, if we take a certain duration here, let's say here, this duration, okay, we can see here that the channel at Bob in this duration is better than the channel at Eve. Eve's channel is degrading, I mean, it's going down, which means it's if you transmit any information, any signal over this period, most probably your signal power will get reduced because the channel is acting like a suppressor, while Bob's channel here is getting amplified. Okay, so this is an opportunity for us when we discover such a thing, a period of time or a bandwidth in frequency where Bob's channel is better than Eve's channel. Bob's channel is better than Eve's channel. In this case, it's an opportunity for us to send our data and our information. Why it's an opportunity for us? Because Bob will be able to decode the message correctly while Eve will not be able to decode it correctly. And the same thing we continue with the other parts of the channel. Here again, okay, now here Eve's channel is better because it's going up. This is because the channel representation here is in power. So as you can see, Eve's channel here is going up, but Bob's channel is going down. In this case, if I transmit any information, Eve will be able to decode it, but Bob will not because his channel is bad. Therefore, I don't transmit over this. I decide not to transmit, which is clever. I detect that if I transmit or send information over here, Eve will be able to decode it. So why should I transmit over there? I should stop. I should wait for a while until my channel condition becomes better, which is this period. Here, I have better channel at Bob, but bad channel at Eve. So I can transmit again here. I transmit here. I transmit here. I transmit in all durations where Bob's channel is better and stronger than Eve's channel, because in that case I can guarantee the quality reception at Bob, but degraded reception at Eve. So this is one example of adaptation. One example. Another example of adaptation. So what's the example here we mentioned about adaptation is on-off transmission based on the channel condition, small scale fading channel condition. We could also use adaptive modulation, for example. Modulation, we have different types of modulation. We have lower order modulation, higher order modulation. The higher the order of the modulation, the more the speed of the internet will be. And when the channel condition is good, I can send higher order modulation, like 64 QAM. But which means 64 QAM, it means in each signal, in each symbol duration, I can transmit 2 to power 6. So it means you can send 6 bits with 64 QAM modulation order. If you have 128 modulation order, how many bits you can transmit? 2 to power 7, which means 7 bits. This is represented by 2 to power 7 is equal to 128, which means you got 7 bits, because we can represent the sequence of data we have only with 0 and 1. That's why we have 2 options. That's why the base here is 2, but the number of bits we can take to represent each symbol is 7. So when the channel quality is good, we can send higher order modulation. Now, higher order modulation, for good channel quality, you can detect it. But when the channel quality is bad, you cannot detect it. And there are certain levels that can be used in order to build a mapping table and decide when to use this type of modulation and when not to use this type of modulation. So we have BPSK, QPSK, 16 QAM, and so on. Okay, tamam. Any questions? So so far so good. Excellent. So the last technique, injection of artificial noise. Here, what do we do here? Let's again draw another channel for Bob and Eve, which is clear uh, in a different color. So this is again Bob's channel. This is assuming this is what the receiver measures. And each channel, I'm drawing a random channel, but it's possible to see it like this. I mean, okay, this is for Eve, E, and here Bob. So in this case, if this is the channel response at Bob and this is the channel response at Eve, one might ask me, why do you can you explain to me why do we usually have different channel responses at Bob and Eve? Why don't we have them identical? I can reply you by saying because they have different locations and they are located in a rich scattering multipath environment like an indoor environment or Wi-Fi. Bob and Eve, they are two separate devices and they cannot be exactly on top of each other. And I told you, if they are away from each other, if they are separate by more than lambda over 2, the space between them is more than lambda over 2, which is in the case of Wi-Fi, few centimeters. Few centimeters. Like even if you put the phones next to each other, one phone is here and the other phone next to it, the size of the width of the phone is more than a few centimeters. So therefore they will experience different channels. And therefore we can draw the channels to be different. They rarely can be really identical. That's why we draw them usually different, and we practically also measure them and find them to be difficult. If we have software-defined radio in the lab in the university, software-defined radio devices, you could measure these channels and see for yourself in practical scenarios how the channel at Bob can be different from the channel at Eve when they are placed at different locations, as long as the distance between them is more than lambda over 2, which is realistic and practical in real life scenarios. It's always few centimeters away from each other. Now, injection of artificial noise. Now, what can I do? I can see, for example, if I look at the first part here, if I look at a part where the channel at Bob is worse than the channel at Eve, this part, for example, I can see here the channel at Eve is better than the channel at Bob. But I urgently need to send information at this duration, at this time period. I cannot wait. Or for some reason, I don't want to waste resources. I want to exploit all the available durations, all available bandwidth to transmit my data. Now, in this case, using adaptation techniques or channel coding, if I transmit my data, the channel is good at Eve here, but the channel is not good at Bob. So what can I do in this case? What can I do? Adaptation will not work because if I transmit something and adapt it based on the channel quality here at Eve is better, so Eve will easily be able to decode the signal because the signal to interference noise ratio is good at Eve, and the condition we need to achieve physical layer security is not satisfied here because Eve's signal to noise ratio is better or stronger than that of Bob. So what can we do in this case? So we can intelligently inject noise that can affect Eve but not affect Bob based on the channel. So when we add noise here, the noise will come and suppress this and make it, because of the interference and noise, and make it maybe like this. And this power no longer as high as this value. So in this case, although Bob low signal to noise ratio is low, but Eve has an even lower signal to interference noise ratio. And therefore, when you subtract this from this will be stronger. So I can find a way to transmit my data here securely. Now, in the coming lectures, we will understand some of these techniques in noise and interfering signal techniques that can achieve that. Okay, where you can intelligently detect this duration and add noise where it can affect Eve but not Bob. So we can have a break here and continue after 5 minutes. Thank you and see you in the next part.